Well, today I'm going to tell you IoT networking consideration and the challenges. What are when we are just implementing the IoT networking, what we should consider and what will be the challenge. When you consider which network technologies adopt within your IoT application, be mindful of the following constraints: the range, the bandwidth, the power usage or the power consumption, intermittent connectivity, uh, interoperability, and also the security. Let's start from the range. Um, Range. This is especially networks can be described in terms of the distance over which data is typically transmitted by the Internet of Things devices attached to the network. Personal area network. If we take the personal area network, it is short range where distance can be measured in meters, such as wearable fitness track devices that communication with Apple app or a cell phone or over Bluetooth low energy. A local area network is short to medium range where distance can be up to hundreds of meters, such as home automations or sensors that are installed with the factory production lines that communicate over Wi-Fi with gateway devices that is installed within the same building. Metropolitan area network is long range, city-wide, where distances are measured up to a few kilometers, such as smart parking sensors installed throughout the city that are connected in a mesh network topology. Wide area network is long range where distance can be measured in kilometers, such as agricultural sensors that are installed across a large farm or ranch that are used to monitor microclimate environmental conditions across the property. So when we are considering the challenges in IoT in terms of range, your network should retrieve data from the IoT devices and transmit to its intended destinations. Select a network protocol that matches the range is required. For example, do not choose Bluetooth low energy for a wide area network application to operate over a range of several kilometers. If transmitted data over the required range presents a challenge, consider edge computing. Edge computing analyzes data directly from the devices rather than from the distant data centers or elsewhere. Bandwidth. Bandwidth is the amount of data that can be transmitted per unit of time. It limits the rate at which data can be collected from IoT devices and transmitted upstream. Bandwidth is affected by many factors, which include the volume of data each device gathers and transmits, the number of devices deployed, whether data is being sent as constant stream or intermittent burst, if any peak period are notable. The packet size of the networking protocol should match up with the volume of data typically transmitted. It is inefficient to send packets padded with empty data. In contrast, there are overhead in splitting large chunks of data up across too many small packets. Data transmission rates are not always symmetrical. That is, upload rates might be slower than download rate. So if there is two-way communication between devices, data transmission needs to be factored in. Wireless and the cellular network are traditionally low bandwidth, so consider whether a wireless technology is the right choice or high volume applications. Consider whether all raw data must be transmitted. A possible solution is to capture less data by sampling less frequently. Thus, you will capture fewer variables and may filter data from the device to drop insignificant data. If you aggregate the data before you transmit it, you reduce the volume of data transmitted, but this process affects flexibility and the granularity in the upstream analysis. Aggregation bursting are not always suitable for time-sensitive or latency-sensitive data. All of these techniques increase the data processing and storage requirements for the IoT devices. Power usage. Transmitting data from a device consumes power. Transmitting data over long range requires more power than over short range. You must consider the power source such as battery, solar cell, or capacitors of devices and its total life cycle. A long and enduring life cycle will not only provide great reliability but reduce operating costs. Steps may be taken to help achieve longer power supply life cycles. For example, to prolong the battery life, you can put the device into sleep mode whenever it is idle. Another best practice is to model the energy consumption of the device under different load and a different network condition to ensure that the device power supply and storage capacity match with the power that is required to transmit the necessary data by using the networking technology that you adopted. Intermittent connectivity. IoT devices are not always connected. In some cases, devices are designed to connect periodically. However, sometimes an unreliable network may cause device to drop off due to connectivity issue. Sometimes quality of service issue, such as dealing with interference or channel contention on wireless network using shared spectrum. Design should be incorporate intermittent connectivity and seek any available solutions to provide uninterrupted service. Should that be a critical factor for IoT landscape design? Interoperability. Devices work with other devices, equipment, systems, and technology that are interoperable. With so many different devices connecting to the IoT, interoperability can be challenged. Adopting standard protocol has been traditional approach for maintaining interoperability on the internet. The standards are agreed upon the industry participants and avoid multiple different designs and directions. With proper standard and the participants who agree to them, incompatibility issue means interoperability issue may be avoided. However, for the IoT standardization process, sometimes struggle to keep up with innovations and the change. They are written and released based on the upcoming version of the standards that are still subject to change. Consider the ecosystem around the technologies. Are they widely adopted? Are they open versus proprietary? How many implementations are available? Using this question to plan your IoT network help plan better interoperability for more robust Internet of Things network. Security. Security is a priority. Selection of networking technologies that implement end-to-end security, including authentications, encryptions, open port protection, is crucial. 802 15.4 includes security models that provide security features that include access control, message integrity, message confidentiality, and reply protection, which are implemented by technologies based on standards such as SIGPI. Consider the following security factors in shaping a secure and a safe IoT networks. Authentication. Adopt secure protocol to support authentication for device, gateway, users, service, and applications. Consider adopting the X.509 standard for device authentications. Encryption. If you are using Wi-Fi, use wireless protected access. For wireless network encryption, you may also adopt private pre-shared key approach to ensure privacy and data integrity for communication between applications. Be sure to adopt transport layer security, which is based on but adapted for unreliable connections that run over UDP. Transport layer security encrypt application data and assure its integrity. Port protection. Port protection ensures that only the port required for communication with the gateway or upstream application or service remain open to external connections. All other ports should be disabled or protected by firewall. Device port may be exposed when exploiting universal plug and play. Vulnerability, especially universal plug and play vulnerability. This plug and play should be disabled on the routers. This is all about Internet of Networking consideration and the challenges. Thank you.